Okay, we ended on this slide, but I didn't totally get to finish it, so I wanted to go through. Again, when we're talking about what will determine if something will actually form a solution, first we're going to look at the solute to the solvent interactions, okay? And they have to be similar in their bonding type when they're talking about likes dissolve likes, okay? The one I didn't get here was the gases over here. They only have one dispersion force. They only have the London dispersion force. They don't have the dipoles. They don't have hydrogen bond, any of that. So the larger the gas, the more soluble it will be. So if you look over here, the largest gas is krypton, and you can see it's much more soluble than like nitrogen. Nitrogen would be the lightest of these gases. So again, the bigger it is, probably doesn't move around as much, so it's easier for the water to dissolve it. Okay, so again, when we're talking about interactions, the solute to solvent, they have to be similar in their bonding type if you want them to actually dissolve. If not, they'll be insoluble. In other words, they don't dissolve in each other. Okay, so if you have organic molecules in water, the polar organic molecules are going to be able to dissolve. Okay, because again, polar meaning they have positive and negative ends. Water has positive and negative ends, so they can dissolve each other. But if they're non-polar, it ain't going to happen. Okay, because you don't have that. Water works by going to the positive and negative ends, so it can dissolve an ionic and other polar. But if there is no positive and negative ends, it can't do its job. Okay, so if you have hydrogen bonding in your organic compounds, what happens is the more hydrogen bond you have, the more soluble it is. If it's just carbon-carbon or carbon-hydrogen, they're not very polar, so the water can't do its job very well. So in other words, you need more hydrogen bonding, like over here, they show about OH groups and so. Then you have a better chance for water to actually dissolve the molecule. Okay, all right. Liquids to liquids, when you're talking about liquid to, because again, when we're making a solution, it's not just a solid and a liquid. Okay, liquids that will mix in any proportion are called miscible. So miscible and immiscible are kind of like soluble and insoluble, but they're very specific. They're only for liquids. Okay, so here we have hexane and we have water, and when you can mix them in any proportion, they're called miscible. Okay, if they don't mix together, like oil and water, okay, then they're called immiscible. So this is, like I said, is kind of like soluble and insoluble, but solubility has a limit. Miscible does not. And miscible and immiscible are only when you're talking about two liquids. Okay, so that's the difference between them. But if you can mix them in any proportion and they will mix together, that's miscible. If they won't mix together, that's immiscible. Okay, hexane is nonpolar and water is polar. That's why it's kind of hard to see, but you can see the hexane stays separate. Water and oil would be like this. But an example of an miscible one would be alcohol and water. You can mix them and they will mix together because alcohol has more hydrogen bonds, so it has a it has the polar end, so the water will work on it. So you can mix alcohol and water as much as you want and they will mix together. But here you can see hexane won't do it. It's nonpolar, so it won't mix with the water. Okay. Okay. Other things that affect, and especially biological importance, things that are important. We have two different types of vitamins. We have fat-soluble vitamins and we have water-soluble. Okay. A fat-soluble vitamin is nonpolar. They're stored in your body, and they can actually become toxic. Okay. Because if you get too much, like vitamin A, in your system, it can be bad because your body will store too much of it. All right, here's vitamin A down here, and it only has one polar group, so it's hard for water to dissolve it. Now, if you look at vitamin C is a water-soluble vitamin. Okay, it's not stored in your body. You have to replenish your vitamin C every day. You don't have to replenish your vitamin A. But again, if you get too much of this, it can be toxic. Not true here. Vitamin C, vitamin E, vitamin K, those ones you have to replenish every day. And you really, even if you're crazy and take loads of vitamin C, it's your body will just wash it out. You're wasting your money because it's all ending up in the toilet, if you know what I mean, but it won't hurt you. Okay. So water soluble vitamins need to be included in your daily diet, but they will dissolve in water, so your body will wash them out. So you'll use what you can, but what you don't need, you'll get rid of. Vitamin A will be stored, and again, that's can be toxic. Most people don't have too much vitamin A in their body. Some people just get crazy, you know how that goes. Okay, another thing that affects whether something will make a solution or not is pressure. Okay, the solubilities of solids and liquids aren't really affected by pressure, but gases in a liquid definitely are. Okay, so if you increase the pressure, you can increase the solubility. That's pop. You know, we're dissolving carbon dioxide in water. We have to have pressure to keep that carbon dioxide in there. If you don't keep that pressure, you lose all that carbon dioxide. It's not going to stay in there if there's a way for it to escape. So we're increasing the pressure, and then we're allowed to dissolve carbon dioxide in water. Okay? So gas solubility is definitely affected by pressure. The more pressure, you're basically pushing it in there. You're, squeezing it in there. That would be increasing the pressure. Okay? Here's Henry's law. Henry's law deals with the solubility of gas and what they call the pressure, a partial pressure above the gas. Okay? It shows you helium, which is a smaller gas, nitrogen, carbon monoxide, oxygen, whatever in their solubility. But basically what happens is, here's a piston, and this one's in equilibrium. They're moving back and forth in equilibrium. If I take this plunger and put it down farther, I'm increasing the pressure. Now I'm increasing more particles, more solid particles to dissolve in the solvent. If I lift it up, okay, I can restore my equilibrium. But now if I move it way up here, or remove it, now I'm actually decreasing my solubility. My solid particles are actually, escaping into the air. So when you increase the pressure, you increase your solubility because you're like pushing them into there, okay? And it's proportional. If you increase this by, let's say, 50, you're going to increase this by 50. They're going to be the same, the amount, okay? And then there's temperature effects. And today I'm going to have you do an assignment similar to this. But when you increase the temperature, in most cases, you increase the solubility, okay? It's not always true, but for most. And if you're talking about gases, it's just the opposite. If you increase the temperature, you decrease the solubility. And if you think about it, if you increase the temperature of the solid particles, then they're going to move faster in a gas and they're going to actually escape. So they won't stay in solution. So temperature, if you're doing a solid and a liquid, if you increase the temperature of the liquid, usually you will increase the solubility. But if you're doing gases, it's just the opposite. And again, because if you increase the temperature of the liquid, these particles are going to start moving faster and they're going to escape. So the best, if you're talking about, dissolved oxygen, like in water for fish, cold is better. Cold holds the oxygen in. If you heat it up, the oxygen escapes. Not so good for the fish because then they basically suffocate because there's no oxygen. Okay, so if I'm reading this chart, okay, so for most solids, as temperature increases, solubility increases. Okay, so what happens here? Let's say I'm doing lead nitrate right here. Okay, this chart tells me that at 0 degrees, excuse me, at 0 degrees, you can see about 35 grams of potassium nitrate will dissolve in 100 grams of water. That's kind of the standard, okay? So if I have 100 grams of water and its temperature is 0, I can dissolve about 35 grams of lead nitrate in there, okay? Under this amount, so if I only add 30, that would be considered an unsaturated solution. It can dissolve more. Above, like if I tried to add 50 grams, well, 15 of it isn't going to dissolve. This is a saturated solution, okay? So you can determine how many grams are going to dissolve at a certain temperature by using a chart like this. And this has been determined through experimentation. Okay, so let's say I have potassium nitrate dissolved in 100 grams of water. Okay, what does the temperature have to be in order for, let's say, 80 grams to dissolve? So here's 80 grams. Here's potassium nitrate. So I go down and between 45 to 50. So if the temperature is about 45 degrees, then I should be able to dissolve my 80 grams of potassium nitrate. Okay? If it's less than that, then again, let's say my temperature is only 30, well, only about 45 grams are going to dissolve. The other 35 grams, if I'm adding 80, aren't going to dissolve. The only way I can get them to dissolve is heat it up. Okay? So that's how you use a chart like this. So you can do one of two things. You can say, oh, I'm going to add 60 grams of calcium chloride. What does my temperature have to be? Well, 60 would be about what? 5 degrees? Okay? If I'm looking here. Okay? So this determines whether it's a saturated solution or an unsaturated. Okay? If you look at salt, here's salt is. Salt really doesn't change when you increase the temperature. At 0, it's about 35. Well, when you warm it up to 100, it's only about 40. So it doesn't change a lot. So salt is one of those. Some of them, like, you can see some of them here, potassium nitrate. Look at when you warm it up, it really increases the solubility. Okay. And here's one, cerium sulfate. It actually goes down. That's kind of a weird one, but when you increase the temperature, you actually decrease its solubility. This is abnormal. The norm is the other way. But again, use a chart. So let's say I want to dissolve 70 grams of potassium chromate. Okay, what temperature? Okay, so I find my potassium chromate. I'd go 70 grams is right here. So I'd go down. I need my temperature to at least to be 90 degrees. Okay, if I say, okay, I have 25 grams of potassium chloride in 40 degrees. Is it saturated or is it unsaturated? Okay, 45 degrees. Potassium chlorate's right here. What did I say, 30 grams? Okay, at that temperature, okay, I said 45 degrees, I can dissolve 40 grams of potassium chloride. Okay, so if I have 30 grams of potassium chloride at 45 degrees, that's definitely an unsaturated solution because I can dissolve up to 40. Okay, so I still have 10 grams to go. So again, this line, at this line, you're saturated. Above it, you're saturated. From here and above is saturated. Below is unsaturated. Okay, and again, the temperature, as you increase the temperature, you increase the solubility. So you can use the chart to do that. Okay, so you can either tell what temperature you need it to be to dissolve it, or you can tell which one's the most soluble. Obviously here, your most soluble is going to be calcium chloride because look at 25, it's dissolved 100 grams. Okay, all the rest of these have to be hotter in order for that to happen. And some of them, it's not going to happen. It's not going to happen for sodium chloride. It's not going to happen for potassium chloride. They don't even get to that point. So again, this is a solubility curve and you use it like that. When you're talking about gases, for all gases, as temperature increases, solubility decreases. Okay, and again, that's because the particles of gas start moving too fast and they escape. There's nothing to hold them in solution, so they just leave. The heavier gases, it increases more as you increase the temperature. So you can see with a gas, when you increase the temperature, you decrease the solubility. And it's the same kind of deal. Okay, carbon monoxide at 30 degrees, I can dissolve a little less than, it's 1 part per million. Okay, that's how you'd read a chart here. But this is the chart you kind of read when you're trying to figure out saturated and unsaturated. Okay, but again, cold is better if you're trying to dissolve, especially oxygen. Fish like cold weather because there's more oxygen in it. Cold water, not cold weather. You know what I'm saying? Okay. There's a video here on solutions. You guys can go back and watch this if you want. I'm not going to spend our lecture time doing that. Then we go, okay. So that's that part. Today I'm going to give you an assignment where you're going to get a chart like this, and I want you to do the questions and send them to me. And that'll be your assignment for today. Okay, so we're done with part 2 of chapter 13.